slideshow. So just going to start out like we're going to go actually into some actual like Python code at some point. So that's part of the fun, I guess. And hopefully everything works okay. I double checked, but we'll just make sure. But I just want to give a little quick recap again, just so we're getting in the right mindset before we start doing this. Because the whole idea is to basically give you just a taste of like what one might do as a data scientist when given a data set. Like what are the things that like the data science pipeline, what do I do when I get data? So just to start again, what is data science for everyone? I think that I've used this slide every single time, but the idea is that data science is it's not like it's a field, but it's basically a collection of skills. And so it sits at the confluence of computer science, math and statistics, and domain knowledge. And includes things like data engineering, model building, visualization and communication, and then problem solving. So really like taking data, cleaning it, doing some sort of modeling on it, evaluating those models, and then maybe understanding what those models are telling us at the end, and then communicating that. So it includes both technical skills and soft skills. And we're going to go through some of that in kind of a technical manner by going through a Jupyter notebook. So for those who are super into writing their own code in Python or R, hopefully it's Python because that's what I'm going to be doing today. But if it's R, that's okay. You'll sort of get what I'm doing anyway. And then just because this issue will come up in there, I just want to talk about how we categorize data when we're looking at it. And typically when we look at data, we're going to categorize it in two types, categorical and numerical. And then each of those will be blocked into two types as well. And so I think maybe I'll just quickly go through these just to give like a minute here. So in categorical data, there's nominal categorical data. So that's just like sets of values. So like brown, blue, gray, and green eye colors, right? So there's no order to those. And then ordinal categorical data are these sets of values that have an order. So it's like a rank or like a level of education achieved or something like that. So those are like a little bit different, right? There's subtle distinctions there. And then in numerical data, there's interval and ratio numerical data. And this is one of those kind of gotchas in some cases. So interval data includes numerical data that doesn't have a true zero. It might include zero. So like temperature, like Celsius or Fahrenheit, they're interval data. You can measure distances between values in Fahrenheit or Celsius, but you can't actually get a ratio. And the example I always say is, you could say that 20 degrees Fahrenheit is twice as hot as 10 degrees Fahrenheit, but that's not really true because how many times hotter is 20 degrees Fahrenheit than -7 Fahrenheit, right? So you can measure the distances, but you can't really do ratios. And ratio numerical data is numerical data that has a true zero, so you can measure ratios and distances. And then we're going to mostly talk about structured data today. So that's like your tabular data sets or databases. And I won't go into unstructured data really, but we've talked about that before. But we're going to be looking really at structured data. And most of the time in data science, you're trying to figure out ways to make unstructured data structured if you're using unstructured data anyway. Okay, and then I'm going to touch just briefly here on the tools of the trade that we're going to go through. So I talked about this before. I have my joke like picture of pandas there. But a lot of these Python tools of the trade that I use include things like pandas and NumPy and SciPy and so on and so forth. And we're going to talk about really just 4 of them today. We're really only going to use 4 of them in any great depth. So with that, I do have more slides, but we'll touch on those later. So let's go to some code. Super exciting. Okay. So here's we're just going to go through this. I put together this notebook and I grabbed a data set off of here on the right side of my screen. You should see UC Irvine's machine learning repository. That's a great place for just getting kind of like example or toy data sets. Kaggle is too. But this is usually one of the places you can go to get an example data set to play around with new tools and such. So here I grabbed this heart disease data set donated in 1988. I thought it was kind of interesting. I chose it. And also I should say, if anyone has any questions, please, come off mic and intervene at any time. But yes, this data set, I picked it in part because there aren't a ton of features here. It says there are 13 features. There are a decent number of examples or like rows. So 300 rows in the data set. It includes both categorical and numerical data. And I noticed that there are a couple features that have missing values down here. Maybe I can make this a little wider. But so yeah, there we go. maybe what I'll do then is we'll just start going through some Python code because people want to see this stuff, at least according to the survey. So on my left side of my screen here, I have, it's a Google Colab notebook, but it's basically just a Jupyter notebook. Maybe that should have been on the tools of the trade, Jupyter. But basically it's a place where I can interactively run Python code, and I can include both like text and visualization and code in one place. So as I go through, I can write code, I can run it, and if there's some result, it can print it to the screen, or if there's like a figure created, it can also print that to the screen. So that's kind of nice. So first, rather than make our life difficult in terms of data loading and pre-processing, I'm going to use the UC Irvine ML repo has like their own Python package. So I'm going to install that first. Oh, we're connecting. We're not connected to an actual compute server yet. There we go. So some stuff is going to pop up here. Okay, and then I'm going to actually import those tool sets that I mentioned before: Pandas, NumPy, Seaborn, and scikit-learn, and then also this UCI ML repo book. Okay. Also, all of these have already been run before, but whatever. Okay. So here, now we're starting to get into the meat of this. I'm going to fetch the data set from this UCI repo using their own Python package. So I'm just saying this heart disease is equal to this fetch UCI repo, and I'm giving it the ID of this repo. And then I'm just telling it to print out some metadata about it. So a lot of this is the same that we can see on the screen here. And I guess maybe I should, now that we're at this point, I should sort of introduce this data set to the extent that I understand it. But basically, it's a set of patients that have been, again, 13 features have been measured about these patients. And then the idea here, the goal of this data set was to predict when a patient has like heart disease on some 0 to 4 point scale. So 0 being no presence of heart disease in the patient. And they don't actually elaborate on what 1, 2, 3, and 4 mean. But they also note at some point that they usually only really want to distinguish between the presence of heart disease, so the values 1, 2, 3, and 4, and the absence of heart disease, so making it into a binary classification. And then we can see there's a list of features over here that they say they have in here, so like age, sex. Sometimes they don't have a good description of them, but CP, and we'll go through that. Rest BPS, so it's resting blood pressure. In the description over here, and all these other different features, and we can actually see that's in agreement with what I just got here in the code on the left. So I grabbed this repo and I printed out some metadata about the data, and it looks like these feature names are matching up with what I'm seeing over here. So that's a good start. At least that doesn't feel too crazy. And some of them are listed as categorical, and some of them are integer. And then it has this description that also matches what we see over here for the most part. So 2 features seem to be missing values. Okay, great. Sanity check passed. So let's just move along, I guess. Okay, so what I'm going to do here when I'm pulling out, I'm pulling out basically the 2 different sets of data from that table. So features, I'm saying pull out the features, and labels, I'm saying pull out the targets from the data. So that's we can see that there's a target down here, which is the diagnosis of heart disease, and then the rest of them are the features. So we can look at this, we'll inspect the data, we'll just make sure everything looks not too crazy. So features.head, I'm just saying look at the top 5 rows in this table and tell me what they are. So I can see they're 0, 1, 2, 3, 4, so that's 5 rows. I have age, sex, CP, all these different features. And I can see there are values here, right? So this is just it's basically a spreadsheet, right? Okay, so there's values. They don't look too crazy here. Nothing looks funky, right? So let's just move on. That looks interesting. And then I can also use this describe function that sort of gives me a summary. So I can see like the counts of rows for each of these different features, and I can see a minimum and a maximum and a mean and such. And then if we go over here on the right, there were those 2 features that said they had missing values. Yep, looks like they don't have as many rows as the other. So there's 299 rows versus 303 for this CA feature and 301 for this valve feature. I'm trying to sort of rush through this, so hopefully it's not too crazy. Then I'll also look at the top 5 rows of this labels set. This is, again, sort of like another spreadsheet. I can see there's 0, 2, 1, 0, 0. Okay, I think we already established, right? There's 0 and then 1 through 4 as values. Okay, that looks about what I would expect. Just to make sure, I'm going to take this little table that I have here, this labels table, and I'm going to call this function called value counts. This is all in pandas right now, I should say. So this is a convenient way of basically just saying, I have this one column here. Give me the number of counts for every possible value in that column. So there are 164 zeros and then several similar amount of the other values. So maybe more conveniently, let's do some more visual inspection. So not just these little tables on the screen here. So I just made 2 quick little functions here from scikit-learn, or using 2 different functions from scikit-learn. So I just had this function that I created called plot numerical. I give it some data, I give it a feature name, and then it calls Seaborn's KDE plot, so kernel density estimation plot. So that's like it's like a histogram. And then plot categorical is just uses a separate thing. So uses Seaborn's count plot function. So just give me bars of the counts for every possible value of a categorical feature. So for example, we'll just go into, we know that our label is categorical at 0, 1, 2, 3, and 4. At least it's seemingly categorical. We're probably going to binarize it, right? But I don't know if there's an order to the 1, 2, 3, 4 if it means something else. So I would need to talk to a domain expert, and I don't have one from this data set in front of me. But okay, just like we saw in this value counts thing, this is basically just a visual representation of that. 164 zeros and then, some number of the 1, 2, 3s, and 4s. But since before they had said up here, right, that most of the time people just care about absence versus presence of heart disease, let's just collapse those into, so collapse the 1, 2, 3, 4 into a yes and the zeros into a no, basically. So what I'm going to do is I'm going to make a copy of my features table, so the one that includes all of the not labeled data. And then I'm actually going to I'm going to slap a label column onto it, and that's going to be, well, to just quickly summarize, it's going to be 1s when it's greater than 0, or it's going to be 0 when it's 0. So we'll just do that. We can go over here, we can scroll over. Okay, yep, I see I added another column, and the label it looks like it's 0s and 1s. Let's just make sure that looks right. And yep, 164 zeros, and I summed up all the others into a single column of 1. So presence of heart disease in this case. So let's just keep rolling. We'll just, yeah, go ahead.
Could I ask a quick question? Just as someone who's never used a Jupyter notebook, I'm curious how many people have. So are all these categories or headers or did you plug all of those things into the notebook, or do they exist as part of the platform?
So all these like headers for so that like on the data, you mean specifically, Whitney?
I'm watching you, so I see it says inspect data, and there was
all of
those. Did
like
you plug those
functions,
in, or is there like a template? Or
most of these are just built-in functions from tools like Pandas. So yeah, I should be like sort of pointing out like so this head function here, this is just comes for free with, so this I guess I should say also, this features thing is it's a data structure, and it's a Pandas data frame. And if I hover over it, I guess like Google Colab has some convenient things. It's this data frame type. And so basically this features thing has these functions that are like built in. So super convenient. And that's why we like to use tools like Pandas, because it allows us to like quickly do things like, okay, hey, here I can call this head function. I didn't have to write it. It just gives me the first 5 rows and shows me what's in the first 5 rows. And then the same for this describe function, and Google Colab pulls up all the documentation. How convenient. But so this describe function also just in that Pandas toolkit, I can call a describe on a data frame, and it will automatically calculate for every column in that data frame. It'll get you counts of values. It'll get you the mean, the standard deviation, minimum, and so on and so forth. So super convenient. And that's like kind of the magic of using all these data science tools, or like what makes data science more approachable these days too, is that there are so many tools where I don't have to like write some extra code that goes through and counts all the different values and computes the mean and then like puts them in a convenient table. Like I can just call all these functions. So there's very little actually, there's very little extra functionality that I add in this entire notebook. Most of it is just using the tools like Pandas and Seaborn. So hopefully that answers the question, Whitney.
Well, let me clear. So
Yeah,
when
yeah.
you get a Jupyter notebook, does it come with those plugins or is that
Oh,
something
yes,
you add to
sort
it?
of. Yeah,
Okay.
so it depends. So in this case, so I'm using Google Colab because so basically Jupyter is like this platform that I can use that I can write code and run code in it, right? And I Python code in this case. And I'm currently connected to some server at Google that's doing like this isn't running on my machine. It's like running over the internet on one of
Okay.
their computers. And so they have all of these packages pre-installed. If I did this locally on my machine, and you can, I would need to, it would take a little extra effort. I would need to set up, like I would need to install some of these packages. But at this first line up here, by saying this import pandas as PD or whatever, and import numpy as NP, and importing these different things, I'm loading all those code modules in right just in these few lines of code, basically,
Okay, that's
if
super
that
helpful. And
helps
then can
answer.
anybody, so is it like, Gmail or is Google Colab, is that
Yeah.
something that anybody can access?
Yeah. Yeah, no, this is
Okay.
a good point. Like all these, yeah, all these things are good questions. Like, there's so many details I could go into,
I'm
but
the
like, yeah,
non-data
like,
scientist, I'm asking the basics.
no, no, this is great. No, this is perfect. So like, uh, often Colab is run from like basically from Drive. So if you use your UW-Madison Drive folder, that and like if you're in a Drive folder, you can like say like, oh, create new document or whatever in the top left. One of those options, it might say like other under it or something like that, but you can say like new Colab notebook, and it'll create a file that you can then just double click on, just like you can with any Google Doc, and it'll be this stuff. And you can
Okay.
connect to one of their remote servers, and we have, I don't know what like our institutional limits are or whatever, but like you can do a lot. It's like for almost every purpose, this will be all you need. And I will say also, without making any promises, we have been discussing the idea of getting something like a collab operating on campus. So, like, maybe you could mount directly to your research drive from in here, and I could call in files not from like, using UCI, but I could say like, oh, load my file from research drive or something like that. And for all I know, SMPH already has a service like this, but we have been talking about that at an institutional level, or DSI has been pushing for that at an institutional level.
Okay.
Um,
Thank you. That's super helpful. And
yeah,
if anyone else has
sorry.
questions, feel free to jump in. Otherwise, I will
Yeah,
let you continue.
yeah, we're just gonna roll, like we'll get through as much as we can get through, but like this is basically what I do. So I just I just wanted to like, and like people really wanted to see, I guess, like some code and stuff. So I was like, yeah, we'll do it. Like we'll just go through and yeah, and again, you can get access to Colab from Drive, even your own personal Drive account, but it might be different for the institutional. Like we might have access to more compute or something. I don't know. But yeah, so I mean, I'll just keep rolling through. Again, please stop me at any time. So there, right? So we have our collapsed label. I'm just going to go through quickly here and like look at a couple of these other features just so I can get a sense. I have all of them here. We don't really need to click through all of them, but okay. So I'll plot age just for sanity's sake. Okay, looks like probably about what I would expect from this data set. I think, if I read there's a paper sort of attached. The paper's a little bit limited, um, but yeah, I mean, this is sort of what I would expect from a patient population when we're looking at heart disease. Um, and then because I attached that label, and I can also like sort of, I added a little extra feature to my numerical plot so I can break it out by the label too. So I can look at, okay, so label 1, heart disease skews higher in age. Okay, that's probably, again, this is more like just me like doing sanity checking. Just be like, does this seem right? I don't know. Probably. And I can do the same for all the other features, and I did that for a bunch. Um, okay. We should actually check like what some of these things mean. They're like greater descriptions. That's another thing that I do. So for example, looking at this CP that I've labeled as chest pain here, if I look at their main variables table here from my domain expert being just this website, there is no description here. So like it's categorical and it's entitled CP and it has 4 values and there are more of them at the 4 end than there are at the 1 end. So what is that actually? So and if there are questions in the chat, if someone else could ping me. But so like what I'm doing here is conveniently I found ahead of time, like I scrolled down, there's additional variable information. I can see CP here comes as feature number 9 from this greater set of features that weren't included in this data set. So I'll scroll down here to the complete attribute documentation. 9, CP, chest pain type. Value 1 is typical angina. Value 2 is atypical angina. Value 3 is non-anginal pain, and value 4 is asymptomatic. So no chest pain, and then 3 different flavors of chest pain. Okay, so this is listed as this is like the first thing that one of the things that I would notice, right, when I'm thinking about categorical versus numerical data. So this is a categorical feature that is encoded as integers 1, 2, 3, and 4, and it is clearly not ordinal, even though one might think that because it's 1, 2, 3, 4. Like maybe you'd think like, oh, increasing levels of chest pain or something. But the answer is no, that's not it. There's typical angina, atypical angina, non-anginal pain, and then asymptomatic. So, okay, probably need to think about that a little bit more carefully, right? I don't want some regression model or something to treat these as increasing values. So this is not ordinal, so I'm gonna deal with that in a little bit, right? Okay, that comes up a few times. I think let's just see. Resting blood pressure is numerical. Okay, sure, looks ballpark like systolic, I guess. Serum cholesterol, okay, that looks about what I know about cholesterol. I think 200 is like pretty good. Fasting blood glucose, oh, that's categorical. Interesting. Let's go back here. Okay, so that was, let's go up here, FBS, feature, categorical, fasting blood sugar greater than 120 milligrams per deciliter. Okay, so this is high blood sugar and not high blood sugar, I guess, right? So good to know. It's not just the fasting blood glucose value. And whatever, again, I can go through this. Well, here's an interesting one, resting ECG. Oh, no description again. So this is the life of a data scientist, right? You're like, all right, I have this feature here, this column, and I might guess what it is because I know what ECG is. So I might be like, oh, okay, it's ECG. But let's just double check. Okay, so 7 is actually number 19 in the documentation here. Resting ECG. All right. Value 0 is normal. Okay, normal. Value 1 is having ST-T wave abnormality. Okay, so this is ST-T wave abnormality. And then value 2 is showing probable or definite left ventricle hypertrophy, whatever. Okay, so another ordinal looking categorical feature, but not, I don't think. Unless if there's a cardiologist here and I'm wrong, please tell me. But it doesn't look like it's ordinal to me. So maybe like, we can just keep going through this. I'll just quickly go through these just because, whatever, it's nice to look at pictures. But that comes up several times where we have categorical features that look ordinal. And then a lot of features that are not, oh, that one I broke out by. Right. Exercise-induced ST depression, labeled old peak. And anyway, whatever. But so here's another one that I had noticed when I was looking at it originally. I had looked at just the distribution by itself, and I didn't know what to take from it. So I broke it out by the label just to make sure, do some sanity checking. And I believe that one would expect this ST depression from exercise to be higher in riskier patients. That was my understanding of just Googling it. I don't understand it well enough. But again, that's why we have domain experts. And we work as data scientists to be able to communicate and to work with domain experts because they can answer those sorts of questions. Slope, another categorical feature that looks ordinal. Maybe it could be treated as ordinal. I don't think so. It's number 41. You're just experiencing me going through and looking at documentation again. So all right, so here's feature 41, the slope of the peak exercise ST segment. So I believe upsloping is good. I don't know if there's a difference between flat and downsloping in terms of badness, but so they could be ordinal, but whatever. We'll maybe treat them as just non-ordinal categorical, right? Okay, and then oh, here was another one. So this is one of our features that has NANs. It only has 4 NANs in it. Okay, so that's not too bad out of 300. And then this thallium heart scan one, which I didn't fully understand, with values 3, 7, and 6, has 2 NANs. Let's actually look at what those values are as well. So this, and I interpreted, I think, thal as thallium heart scan. So number 51. Yep, just says thal, 3 equals normal, 6 equals fixed defect, and 7 equals reversible defect. I don't know what those are, but they're clearly not ordinal, and it's not numerical, but it's a 3.0, 7.0, and 6.0. Just another data set that we got that has something weird in it, and fortunately, we can deal with that a little bit. But at the moment, I need to decide what to do with my NANs, right? So I have 4 NANs for this CA feature. I have 2 NANs for the thallium heart scan feature. I think I could do things like you can often say like, oh, we'll just insert the average value, or like you can try to match them with something else and take the most likely value based on other features and insert it in there. So these are just like missing values, right? But I'm just going to drop those examples. So I'm just going to lose 6 rows of my data set. And that's okay, I think, in this case. But again, I would talk to a domain expert and I would, see if they agree with that decision. But so here I'm going to use, again, as I was saying before, like I'm going to use one of these features that are already pre-built into pandas. I'm going to say, tell me which rows are not NaN in this CA column, and select those and replace my old data set with those rows, the ones that are not NaN, and then do the exact same thing with that thal feature. So now I can see, so I had 303 rows. Here I can see after I selected for the not NaN rows, I had 299, lost 4 rows. And then after I selected for the not NaN for the thal column, 297 rows. Okay. Any questions about stuff, or as I saw some things pop up in the chat? How are we doing, everyone?
So the couple of things that popped in the chat, Mariana was asking if, I don't know if you can see the chat, but if that's the right link to the Google Colab.
Oh, this one?
You can verify. She put in the
Oh,
chat,
I see. Yeah, like so that would be like the main yeah, so that's I don't know if that's like that'll probably get you somewhere where you can create a Colab notebook. I usually just do it in Drive, but that'll at least tell you what Colab is and gives you like information about all the features for sure. But yeah, that's the one. Super
and
handy. Yeah.
then Chris asked, she made more of a comment, but sort of inferring that, so she often works in SPSS, actually, as do I. And she says it looks like you have more control over specific queries. And then related, Jennifer asked, do you prefer notebooks in Collab or Visual Studio Code? So sort of what are the
Oh,
differences between different platforms, and then the difference between
yeah.
Collab and Visual Studio Code?
Yeah. Well, all right. So first, like I can't quite answer the question about the SPSS thing. I don't use SPSS, so I know that I have like great control over what I'm doing here, and it just sort of depends on the amount of time you want to put into like writing your own really custom code to do stuff. And I do that a lot when I'm really like getting into the nitty-gritty. I'm often writing a lot of custom code to do very specific things. And then in terms of like, do I prefer Colab versus like VS Code or something? I don't use VS Code a lot. That's not because I don't think it's a great tool. A bunch of my colleagues use it a ton. It's probably more feature rich in general. Like it's more appropriate for just general programming. Like if you can write C and C++ and whatever you want, like any language in VS Code. I think they have interesting features for like incorporating Docker containers. So if I were to create some tool in the code that like you know, takes in some input and spits out some output, I could make that into this Dockerized container, which is a whole other seminar to talk about Docker. But like there's all sorts of like features to VS Code. I think the traditional or the typical advice that one should give, and I think this is still generally true most of the time, is that the correct tool for the job is the one you're most comfortable with that can accomplish the job. So sometimes it's worth it changing, but for the most part, like if you're a VS Code user and you're comfortable with that, go with that. And it probably is a little bit more feature rich. So sometimes it might be like there's just something I can't do in Colab. For the most part, for all basic data science stuff and like some basic machine learning stuff, Colab's probably going to carry enough weight to just do all that stuff. And I don't have to worry about managing package versions and things like software module versions and things. Um, but uh, but yeah, I don't know if that's a good answer to that question, but at least is an answer. And please feel free to interrupt and ask more specific questions if you want to drill down. Um, but I guess what I'm going to do though now, we're just going to keep rolling. Oh, I saw the chat pop.
She said it's
Okay, great.
helpful.
Perfect. I'm glad. Okay, so what I'm going to do is for this now we're just sort of getting into this point where like I dropped my NAs. Now I have all those categorical features that were like maybe slightly weird. Like they aren't ordinal, but they look kind of ordinal. So I'm going to go through and turn all my categorical features, which are encoded as like integers or floats in some cases, and I'm going to turn them into categorical features using this. Well, it's a function of pandas called get dummies. Basically, I can take a single column that has integral values or like numerical values in it, and I can say, hey, pandas, this is actually a categorical feature, so please split that into binary columns. So if there were three possible values in categorical, please split that column into three different columns that are binary to represent those different values. So here I wrote some extra code here again, customizing what I want to do. But basically I have this function that I wrote called split categorical features, and I'm going to pass it my data set here, and I'm going to tell it to split the CP feature, and value 1, I want it to be sort of like extra labeled as ANG for angina. Where'd that go? It's up here somewhere. So that's typical angina. 2, label it with atyp angina. 3, non-anginal, and then 4, none. Maybe it should be asymptomatic. None seems maybe whatever. But we can see like after I did that, I no longer have a CP column, but I have these 4 CP underscore columns. So CP ANG, CP atyp ANG, and so on. And I'm just going to do that repeatedly. So resting ECG, I wanted to split that one out too because it's not ordinal, and seemingly it's not ordinal to my intuition at least. So split that one into those 3 different possible values. So now I have 3 new columns, and I lost the original rest ECG column. Same with this slope one and this thou column. Great. So now I can see at the end of that, I have all these extra binary columns on the right here. Okay, so I think I have 23 columns now. So I have 22 features and 1 label in this data set. I have 297 rows, just like I expected. And now let's just quickly do some very simple machine learning stuff because we did all the data processing. There couldn't possibly be more problems we would ever run into, right? Like all of this is an iterative process is the point.
Hey,
But yeah,
Finn,
so let's just do some.
could I ask
Yeah,
a
yeah,
quick question? Just thinking about
yeah.
the relationship between the data scientist and the non-data scientist. So you've mentioned a number of times that there were points where you were unsure of things, and you mentioned
Yep.
to reach out to the domain
Yes.
scientist. So just thinking
Yep.
about that relationship. So is that what often happens? You get a data set and then they said, help us, and you clean it and look at it in exactly the way that you're walking us through it right now?
Pretty much. Like I
Okay.
mean, it's a little bit more in depth. Like in this case, like I had a data set that already had a bunch of work done, but like it might go all the way back to where I would be talking with, well, for example, talking with Beth and during my dissertation work. And at that point, we're starting from like, you know, an EHR basically. So like, all right, so I have this electronic health record. We care about 7 things of the bazillion that are in there, and some very smaller, like much smaller subset of the population. So there, we have to talk about like, okay, well, how do we first like what features in this or what like tables in this database can tell me which patients I care about. And maybe it's like I get some list of medical record numbers or something like that. But then I even need to like pull out things like I would be inventing features, sort of like it'd be like, oh, all right, so I need to talk to either Beth or some database administrator to be like, maybe I wanted fasting blood glucose or something. Where is that in the database? Okay, now I'm like writing SQL queries or something to pull out for my medical record numbers of interest, my included patients. Now I'm going to pull out fasting blood glucose for some point in time. There's like basically it's like way more involved, but it is like a back and forth for frequently like a majority of the time is typically spent in the data processing step. So like this might be like weeks or months where I am like building the data set that I just pulled in one line up above at the top. Um, and then even then, once I've done that, once I've, have an initial data set, doing these things that I'm doing here, where, again, I've pulled things from the database, I have a good understanding of what I'm pulling and like how I'm sort of labeling it, at least as it relates to the EHR or something. But now I just like look at values and like, oh my gosh, this doesn't make sense. Maybe I find out that those fasting blood glucose values that I pulled don't make any sense. Maybe they're like, you know, 7 or something, like, or maybe I find out there are like 4 different possible values. That's not great. If I thought it was numerical. So like it's a really iterative process where you're going back and forth between domain experts and like other researchers or like administrators or something to just figure out what you can even pull or what you need to pull. And then you even go down into the model, and actually we'll see this, but then you do like some modeling even, and you might run into other things where you're like, oh, that doesn't make any sense. Why is that the case? Like it looked through my sanity checking, like that everything looked fine, but something maybe doesn't make sense. And now we have to go back and try to figure out why that's happening. So like it's a you can start from all the way at the very beginning and go all the way to the end and be like, whoa, wait, something's wrong, and go all the way back to the beginning, or but like usually your cycle is shortened. But does that answer your question? Sorry.
It does. And actually, I was going to, next question I was going to ask that I'm only sharing because I was going to say, what's the one thing that you need from your non-data scientist when you're working, or your domain scientist? But I think I'm hearing it's not one thing. If there's one
Right.
thing, it's to be open to having these
Yes.
ongoing iterative dialogues to make sure you get the product just as a
Yes.
label, just as some word to capture what all of this is, to get the product
Yeah.
that you need.
Yeah. And like, that was helpful for me in my dissertation work that Beth was very open and very data minded. Uh, like like basically you want to be conversant in the domain if you're the data scientist, and ideally you want your domain expert to be at least somewhat conversant or patient with you. So like there's always back and forth, and like sometimes it takes a lot of time to like both build a rapport and like a relationship. um, there's a ton of soft skills involved. Like it's not just like, I guess people talk about this all the time in like industry, right? Like, oh, the engineers just think, wow, they just think this way, and like, oh, the salespeople just think this way or whatever. Like, you have to like find the middle ground so you can actually communicate. And this is just true in all human relationships, but it's a very human relationship when you're doing this kind of work. So yeah.
Okay. Excellent. I'll let you go ahead and run some models then,
Yeah,
and
yeah.
I'll
Yeah. And this will all be very, very fast stuff too. So we'll like, I guess, yeah, just to do some really quick modeling, super quick and dirty, like no, we're not going to be super careful. Statisticians in the room, or I'm not even going to do any stats, but like, please forgive me for the sins that I'm going to commit here. So, first, all I'm going to do is I'm going to go back and I'm going to take that feature label data set that I've cleaned up in a way or whatever, and I'm going to pull out the columns that are just the features, the things that I want to use to predict this heart disease. So what I'm doing here is I'm just saying features, it's the set of the columns from this feature lab minus the one entitled label. And then I'm just going to sort them alphabetically and print them out. So there they are. I don't see label in here, but it looks like my list. I'm happy. So labels, I'm just going to manually create that. That's a list of names, and it's one long, and it's label. So then what I'm going to do also is, so I have my features. All right, so now I'm going to pull out my features into one, like the actual values into one big matrix. So I'm going to say X equals feat lab, which is that data set that has everything, including my features and my label, and pull out those columns in our list of features. Print that out. Okay. I have 297 rows and 22 columns now. Great. So I'm missing the label column. Good. That's what I want. But when I do the modeling, I only care about the values inside the matrix. I don't care about the row heading or the column heading. So I'm going to use this function. This is a NumPy, or like it's a pandas thing, but I'm going to convert it into a NumPy matrix. And it's not that different, right? 63, you can see 63, and there's 150, 145. That looks like, yep, that looks like the things I'm seeing up here, but it's just without the extra heading information. So this is just the numbers in a matrix. And then the same thing I'll do with my, for Y. If you remember from way back when, I was talking about X as being the inputs and Y being the outputs. Okay, so that's my label column. And then I'm also going to convert that just into a list of zeros and ones. And yeah, and that looks about right. 0, 1, 1, 0, 0, 1, 1, 0. Probably do more sanity checking, but it looks right. Okay. So now here's where I'm going to totally gloss over cross-validation. So if you remember from way back when, what we would love to do if we were evaluating, I guess we could go to slideshow, is we would have one big lump of training data, and then we would fit some model on it, this fx equals y, some machine learning model that predicts y from x. And then I would take a whole new, brand new data set, and I would pump it through there, and I would see if we got the answers right. Never going to happen. Too expensive, too slow. So what we do is typically, or frequently, is this thing called cross-validation, where we break our data set into chunks. Here I have what's called 5-fold cross-validation. So I broke it into 5 chunks, and I'm going to train my A model, 5 times. And each time I'm going to train the model on 4 chunks here and test it on 1 chunk. So I'm training on data that that the model will see, and then testing on data that the model didn't see. And as long as I'm careful about that, everything's good. We can get a rough sense of how that model is able to predict our label from that data set. And conveniently, that would be a little bit complicated to do in custom code. Scikit-learn does it in 1 line for me. So I can tell it, hey, I want to do the stratified k-fold cross-validation in 10 folds, is what I did here. And just, here we go. I have this little stratifier object thing. And so now I can just pass that along to these other little convenience functions that can run. So here I'll use a linear support vector machine. Here it's just running, blah, 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 running. And what it's going to do is it's going to train 10 linear support vector machines on my X and Y using my stratified k-fold cross-validation for the cross-validation element here. And it's going to get me accuracies and recalls and precisions. That's what I told it to send back on my held aside data, on like my validation data. And I can just print out like what are the average results across those 10 folds. Average accuracy is 80%, average recall is 80%. Okay. And I'll do the same thing for random forest and decision trees, just because that's nice to do a few different algorithms to get a sense. Very quick, right? This is just all running super fast. None of these models are super complicated, and this data set isn't gigantic. It's just real quick. And then random forests are nice. They're usually really highly performant. Looks like similar accuracy and recall as support vector machines. But we'll just do a decision tree for fun. And we are reaching the end, so we're going to be tight, but we'll make it. I just wanted like a couple other points to make here.
Can I ask a quick question, Finn?
Yeah,
Is
of
there a
course.
minimum size for a training data set?
I mean,
Chris asked that question in the chat.
yeah, I mean, like, yes. So it's pretty low. It all sort of depends. Like, ideally, you're going to have it. So it depends on a lot of things. One, it like depends on like how many features did you measure and how many labels are you trying to predict. Like, if you were trying to predict, even this is like overselling it, but like if you're trying to predict 5 different types of classification, like maybe it's not a binary thing like heart disease or not. Maybe it's those 0 through 4 labels. Like I'm not going to be able to really do it if I have one example of each, right? Because I just haven't sampled the possible space. But like, like when you again, it's all sort of like squishy and depends on the number of things you measure and so on, and like the algorithms you're using. But I would want to see like ideally, I don't know, in this case, maybe like 10 examples of each at a really, that's like the extreme. But I feel like It's like a gut thing. I don't know. There are minimums, but I don't think you can really calculate it. Like you can calculate those things for when you're talking about like power calculations, like in statistics, but I think in this case, um, yeah, ideally you're on the order of tens or hundreds. Is like the easiest gut check I can say. Sorry.
No, that's good. That you got a thumbs up on that. And then I'm curious because you're running all these, what it looks like different models. And
Yeah,
I see for your decision tree, it says the accuracy is 0.8. Does that mean that that's how well the model predicts heart disease? Like, or is
that's
that what
yes,
that
that's
model
how
means? Is that what that number
right.
means?
Yeah, and so like just to go back, and there's so many details here. Yeah, so like it's 80% accuracy. So 80% of the time it is getting its prediction correct for any one example that it looks at. That's a held aside example. It is able
Okay.
to say like that one with 80% probability it's going to get that one right is sort of how you can say it. And the reason I'm not too worried about this 80% right here is because if you remember from back earlier, our class distribution is actually not super skewed. We have roughly even numbers of positive and negative after we rolled up those the heart disease um, labels up together. So like, but if it were like really skewed, if it were like 90% of my examples were negative and 10% were positive, and I got a 90% accuracy result, I'd be very skeptical because you can get 90% by just labeling everything as negative.
Okay.
Whereas in this case, it'd be closer to 50-50 if you just labeled everything one particular label.
And
Um,
then one other quick question I
yeah,
have, because I know we're running out of, so right now we're evaluating the model, and I'm curious, and I don't know if you'll get here, maybe that's the cart before the horse, is what does this tell us? What does all this tell us about heart disease?
yeah. No, this is so. Yeah, we'll get there. Let me
Sorry if
fast track then.
I
No,
jumped
no,
to the
no.
punchline.
No. It's great. Because I think so. The nice thing is like support vector machines do great. Random forests do great. I put decision tree in here because decision tree is like a much simpler, like not a usually isn't as performant as like an ensemble model like random forests or maybe like one of these like higher dimensional models like a support vector machine. But and I'll just pull out whatever. I'm going to give you an ROC curve because I can. I pulled out one of these models from the 10 that it trained, and I'm just going to quickly just pretend like I explained it. Yeah, let's skip it actually. Like we can talk about ROC at another time because that's going to take up time. Let's just go to your question, Whitney, which is basically like I have these three different algorithms that I ran, and like they're all doing pretty similar. They're all getting accuracy of 80%. Their recall is 80%, 80%, like 70%, where recall is the number of or the percentage of the positive examples that you at least put into the positive bucket. So you like low recall is really bad, probably in disease prediction. But anyway, but the nice thing about models like decision trees is that you can immediately actually look to them and say, like, what did you do here? Like we talked about this 2 times ago, decision trees a little bit. Like we were splitting on features in this, it was a two-dimensional space at the time, but basically I can come up with rules or like a flow chart. It's a decision tree, right? I can come up with a flow chart and I can interpret that flow chart and see if it makes any sense whatsoever. And first order of business, there's this quick little plot tree function in scikit-learn, and I can give it a decision tree, and it plots and prints out some tree thing here. And it's not great. It's okay for getting a rough sense of it, but it is not easy for a human person to read. So what I did is I hopefully correctly converted that tree into a decision tree that is maybe easier to read. So first, like the basically what this tree is saying, like if I look at a patient right now and I say, is there like that thal test? Is it normal? Yes. And did we see no blood vessels on some fluorescent test thing that I don't understand? Um, yes. And their blood pressure is below 157. Yes. Then they have about a 7% chance of heart disease of my patients. So cool. Okay. And if there's a cardiologist in the room, you tell me if that sounds crazy or not. But I will, in the last like minute here, I will say there were a couple of things in here that jumped out at me as weird. So like, all right, so normal thallium test, yes. No, you saw more than zero vessels on this fluorescent test. So okay, we go left here. and the patient has no chest pain, or at least they're asymptomatic for like angina or, you know, the atypical angina, the chest pain thing, then they have a higher chance than if they had chest pain of some sort. So either that's interesting or it's wrong and I should go back. So there are a lot of different potential explanations for that, but this is, in conclusion, we'll say basically this is where we got to, and we got all the way through the life cycle to some sort of like visualization of a decision tree. And I would show this to a domain expert, and I would say, that doesn't fit my intuition. Does it fit your intuition? Or is there a way we can explain that? Or do we need to go back to the drawing board? And with that, I will conclude exactly on the button and answer any questions that people have. And I'll just put this up because this is the most important thing. Always compare to the standard of care, no matter what you're doing. Well, if it's in this space.